Right now, somewhere on Earth, a rock the size of your fist is boiling enough water to power a city of 1 million people. Not metaphorically, literally. And the only thing standing between that rock and a catastrophe that could make Chernobyl look small is a metal rod the size of your arm. That's not a simplification. That's actually how it works. And by the end of this video, you're going to understand every single layer of engineering that makes it possible, from the ceramic pellet smaller than your fingertip, all the way up to the 600-ton steel vessel surrounding it, and the meters-thick concrete dome around that. We're going to go deep, and I promise you, the deeper we go, the stranger it gets. Let's start at the beginning, with the fuel. Uranium is 33,000 times more energy-dense than oil, 43,000 times more than coal. A single ceramic fuel pellet, about the size of a pencil eraser, contains as much energy as 1 ton of coal, or 150 gallons of oil. A reactor holds 18 million of these pellets. The math on that is almost offensive. But here's what most people do not know. Raw uranium pulled straight out of the ground is nearly useless. Only 0.7% of natural uranium is fissile, meaning capable of sustaining the chain reaction you need to generate power. So before a single atom splits, engineers have to put that uranium through one of the most technically demanding industrial processes on the planet. The uranium is mined, crushed, chemically processed into a powder, then converted into a gas. That gas is then spun at enormous speeds inside a device called centrifuges, thousands of them running in sequence, to gradually concentrate the fissile component from 0.7% up to between 3 and 5%. That process is called enrichment. And it is the same process that, taken further, produces weapons-grade material. The difference between a power plant and a bomb is largely a question of how long you run the centrifuges. That is a fact worth sitting with. Once enriched, the uranium powder is pressed into small ceramic pellets and baked at over 1400 degrees Celsius. Hotter than most metals melt, producing a material harder and more chemically stable than almost anything in industrial use. These pellets are stacked inside metal tubes about 1 centimeter in diameter, made from a zirconium alloy. Why zirconium? Because it is extraordinarily corrosion resistant, and critically it absorbs almost no neutrons, which, as we will see in a moment, matters enormously. These tubes are sealed and bundled together into what is called a fuel assembly, and loaded into the reactor core. A single reactor holds between 121 and 193 of these assemblies, each one about 4 meters tall. A fuel load like this will run continuously for 12 to 18 months before 1/3 of it needs to be replaced. Now, here's where it gets interesting. Here's where the engineering goes from impressive to genuinely extraordinary. Inside that reactor core, something is happening at a scale that is almost impossible to visualize. When a neutron strikes a uranium-235 nucleus, the nucleus splits, releasing heat, radiation, and 2 or 3 new neutrons. Each of those neutrons can strike another nucleus, releasing 2 or 3 more, which strike more nuclei and which release more neutrons. In an uncontrolled environment, this chain reaction doubles, then doubles again, then doubles again, growing exponentially until the fuel tears itself apart in a fraction of a second. That is a nuclear weapon. In a reactor, engineers need to do something incredibly precise. They need to maintain what is called the multiplication factor of exactly 1. For every neutron that splits a nucleus, exactly 1 of the resulting neutrons must go on to split another, not 1.1, not 0.9. 1, if it climbs above 1, the reaction grows. If it drops below 1, the reaction dies. Holding that number at exactly 1, continuously, across millions of simultaneous fission events, is the central challenge of nuclear reactor engineering. And the tool engineers use to do it is, on the surface, almost laughably simple. Control rods. These are long rods made of materials like boron, cadmium, silver, and indium, elements that absorb neutrons the way a sponge absorbs water. Insert the rods deeper into the core, and they soak up more neutrons, slowing the reaction. Pull them out, and more neutrons are available, speeding it up. The entire power output of a reactor, from 0 to over 1,000 megawatts, is managed by raising and lowering these rods by centimeters. The most powerful energy source humans have ever harnessed, throttled like a dimmer switch. But there is a crucial engineering detail here that most people miss. In a pressurized water reactor, the control rods are held up by electromagnets, not pushed down by motors, held up. That means if the plant loses power, if anything at all goes wrong electrically, the electromagnets release, and every single control rod drops into the core simultaneously under gravity alone. The reactor shuts itself down without any human input, without any electricity, without any moving parts being activated. It falls. Physics does the rest. That decision, to make the safe state the default state, is one of the most important engineering choices in nuclear history. Now here's where most people think the story ends. The rods drop, the reaction stops, crisis averted. But this is actually where the most dangerous part begins. When the chain reaction stops, the heat does not. Inside spent fuel, radioactive fission products continue decaying, and that decay releases heat. Immediately after shutdown, this decay heat is running at roughly 7% of the reactor's full operating power. On a 1,000 megawatt reactor, that is 70 megawatts of heat with no reaction occurring. Within hours it drops significantly, but it takes days to reach safe levels. Days during which the core must be continuously cooled, or the fuel melts. This is decay heat. And it is the problem that has caused every single major nuclear accident in history. 3 Mile Island in 1979, Chernobyl in 1986, Fukushima in 2011. At their core, each was a cooling failure. So engineers built the Emergency Core Cooling System, ECCS. This is a redundant, multi-layered network of pumps, valves, tanks, and pipes designed with one purpose: to flood the core with water no matter what. Multiple independent trains of equipment mean that if one fails, the others take over. High-pressure injection systems, low-pressure injection systems, passive gravity-fed tanks that need no pumps at all, and at the very end of the line, batteries. Banks of batteries capable of powering critical systems for hours, even with complete loss of all external power. Modern designs like the Westinghouse AP1000 go even further. They use passive safety systems. No pumps are required, no valves need to be opened, no operator action is needed. Water sits in elevated tanks above the reactor. If cooling is lost, the water flows down by gravity. Air flows through ducts by convection. The system cools itself using nothing but the laws of physics for 72 hours, without a single person doing anything. That's not a backup plan. That's the primary plan. But to understand why all of this cooling infrastructure is so critical, you need to understand what it's protecting. And that means going inside the pressure vessel. At the center of every pressurized water reactor is a steel vessel roughly 11 meters tall, 4 meters in diameter, with walls up to 19 centimeters thick. It weighs over 600 tons. Inside, water is kept at a pressure of approximately 2,200 pounds per square inch. That's more than 150 times atmospheric pressure, which keeps it liquid even at 320 degrees Celsius, nearly 20 degrees above water's normal boiling point. The engineering tolerances required to keep a vessel at this pressure, at this temperature, continuously for 40 years are extraordinary. And here is the part that should genuinely unsettle you. That vessel is being slowly destroyed by the very process it contains. Neutrons streaming out of the fuel assemblies are constantly bombarding the steel walls. Over decades, this neutron bombardment makes the steel progressively more brittle. Engineers monitor this process continuously, using test samples embedded in the vessel walls specifically to track how the material is degrading. The vessel that is keeping 300 degrees Celsius water at 2,200 pounds per square inch from flashing into steam is slowly, irreversibly becoming more fragile. Managing that degradation over the life of the plant is one of the quieter engineering challenges in the industry, and one of the most consequential. Now, step back from the pressure vessel. Step back further, because it is not alone. Surrounding it is the reactor building itself. This is where nuclear engineering goes from impressive to almost absurd in its ambition. The containment building, that iconic concrete dome, is not just an architectural feature. It is the fourth and final barrier between the radioactive core and the outside world. The first barrier is the ceramic fuel pellet itself, which traps most fission products inside its crystalline structure. The second is the zirconium cladding around the fuel. The third is the steel pressure vessel. The fourth is this dome, built from reinforced concrete up to 5 feet thick, lined on the inside with steel plate, and engineered to withstand internal pressures of up to 80 pounds per square inch from a steam explosion inside. In 1988, Sandia National Laboratories tested whether a containment structure could survive a direct aircraft impact. They mounted a jet fighter on a rocket sled and drove it into a large reinforced concrete block at 482 miles per hour. The nose of the aircraft crumpled. The concrete showed a dent less than 2.5 inches deep. Modern containment designs are built to standards at least as demanding as that. Every 15 years, each nuclear plant must conduct a containment integrated leakage rate test, pressurizing the entire containment building and measuring how much air leaks out. The acceptable leakage rate is fractions of a percent per day. If it fails, the plant does not restart until it passes. Now, once all that heat is safely contained and managed, something has to be done with it. Because ultimately, and this is the part that surprises most people, a nuclear reactor is at its most fundamental level a very sophisticated way to boil water. The superheated, pressurized water in the primary loop flows through a steam generator and transfers its heat to a secondary loop of water on the other side. The secondary water flashes to steam, which spins a turbine that drives a generator. The steam is then condensed back into water and recirculated. The radioactive primary loop never touches the secondary loop. Not a single radioactive molecule touches the turbine, the generator, or the cooling tower. That cooling tower, the giant hyperbolic structure that most people associate with nuclear power, is simply where the waste heat from the secondary steam is released into the atmosphere. The white cloud billowing from the top is not smoke. It is not reactor steam. It is not radioactive. It is ordinary water vapor, condensed humidity. The same thing you see on a cold morning when you breathe out. The towers themselves are engineering marvels in their own right, up to 200 meters tall, with concrete walls in the middle section that are less than 18 centimeters thick. That thinness is deliberate. The hyperbolic shape gives the structure its strength, the same way an eggshell is strong despite being thin. There is, however, one part of the nuclear fuel cycle that no cooling tower, no pressure vessel, no containment dome can solve. That is what happens to the fuel when it comes out. Spent nuclear fuel is some of the most dangerous material on Earth. When a fuel assembly goes into the reactor, it is mildly radioactive. You could stand near it with minimal protection. When it comes out 4 years later, it is a completely different story. The fission process has transformed the uranium into dozens of highly radioactive isotopes, some with half-lives measured in hundreds of thousands of years. The assembly is now intensely radioactive, intensely hot, and must be kept submerged in water for at least 5 to 10 years, just to cool down enough to handle. The world has accumulated over 400,000 tons of spent nuclear fuel. The United States alone has produced about 90,000 tons since the 1950s. And right now, essentially all of it is sitting in cooling pools at reactor sites around the world, because no country has yet opened a permanent underground repository. Finland is closest, with their Onkalo facility designed to store waste safely for 100,000 years. Think about that number. 100,000 years ago, modern humans had just arrived in Europe. The engineers designing Onkalo have to account for the possibility that the civilization that built the waste may not exist when the waste finally becomes safe. But here's the thing. Some of the engineers building the next generation of reactors believe we don't have to wait that long. They believe the answer to the waste problem is to burn it. Generation 4 reactor designs, including molten salt reactors, fast neutron reactors, and small modular reactors, can use spent fuel from conventional reactors as their fuel source. They extract atom energy from the waste while destroying the long-lived radioactive isotopes in the process. In September 2024, Natura Resources received the first U.S. construction permit for a liquid-fueled molten salt reactor in history. Seaborg Technologies is developing a compact molten salt reactor that can run for 24 years without physical refueling. Globally, 74 small modular reactor projects are currently in development, with over $15 billion in financing committed. The Nuclear Energy Agency estimates that meeting 2050 net zero targets may require up to 800 gigawatts of new nuclear capacity, more than double everything built over the last 6 decades, combined. There's one final thing worth saying. Every layer of engineering we've walked through today, the passive safety systems, the 5-foot containment walls, the gravity-fed control rods, the redundant cooling trains, the materials chosen down to the atomic level, none of it appeared in the original reactor designs of the 1950s. Almost all of it was added, redesigned, or fundamentally rethought in response to accidents. 3 Mile Island gave us better operator training and tighter emergency protocols. Chernobyl demonstrated what happens when you build a reactor without a proper containment building, and with a design that becomes less stable as power increases. Fukushima proved that backup generators sitting in a basement are not sufficient when a tsunami is involved, and it triggered a global redesign of passive cooling standards. Each disaster was a terrible cost, and each one made the engineering better. Inside every nuclear reactor running today is the accumulated lesson of 7 decades of failure, redesign, and refinement. They were engineers who looked at the most powerful force on Earth and said, we can control this, we can make this safe, we can make this reliable. And largely, remarkably, they were right. The rock the size of your fist is still boiling water. The metal rod is still holding the reaction in balance. And somewhere right now, a city of 1 million people has no idea how close to the edge their electricity was generated, or how much engineering stands between them and the alternative.